Thank you. It's a real pleasure to be here, be invited here. Happy birthday. We just posted this paper. I've never worked in billiards before. I bought Serge's book on billiards last year. It's a wonderful book, and I'm a neophyte, but I hope you'll enjoy. So to start, I want you to think of 3 wires in the room, and they're silver coated, and light bounces off, huh? And the only rule is the rules of reflection. I'll write them down more carefully later. So the angle coming in is the angle going out, but it can go out in any direction. And then, so a first question for you to think about, suppose I put them at the coordinate axes. How many reflections are possible? Just to start thinking. How many reflections I will call collisions. Okay? So there's a problem to start. So now I'm going to be formal with what I mean by this. So I'll have a Euclidean vector space with an inner product. And I'm going to take a bunch of linear subspaces in the vector space, and they can be codimension bigger than 1, huh? That's what makes it interesting. They don't have to be hypersurfaces. And so my table, well, first the collision locus C is just the union of all of these. So it's a hyperplane arrangement, if you well, that's not hyperplane. It's a bunch of subspaces. So think of the complement of these axes. I mean, think of all those axes. And then the table is, so that's your billiard table. Think of that as your billiard table. Huh?
Sorry, are all the L's in the same dimension?
That's my favorite case. There's no need for most of the theory, but all the applications, so it's good to think of that as D is the codimension of L, and just think of that as a number greater than 1. Okay. So this is a funny situation. I forgot what the room was like. I prepared slides. I like Blackboard better, so I want to now give you the motivating example. This at a conference in Beers, I think it was 4 years ago, Andreas Knauf, who I've known for many years, he's from Berlin, Fejoz is in Paris. He gave me this question he called train correspondences, and he asked me to work with him on it. And so I'll just tell you where the motivation comes from. This is Knauf's idea. I'll tell you in 2 parts. So first I will tell you what this has to do with the n-body problem. So I call it n-body billiards. So then E is let's do it generally. It's n copies of RD. So usually D is 3. And the L's, I call them delta AB. And there were 2 of the particles collide. So in terms of point particles moving, it's where 2 hit, huh? So 2 of these guys hit each other. Okay? So that's the that's this. Oh, the metric. There's a metric on here. It's called the mass metric. So that if you take 1/2 v, it's the usual kinetic energy with the masses in it. Huh? So these are in RD, each of these. This is in RD. Huh? So this is the motivating example came from here. And maybe before I go into the motivation, I'll just write down the rules. I think that's a good thing to do. Well, I can say the motivation in words quickly, and then I'll do it again. We're going to play billiards here, and then what we want to say is in a certain limit, a positive energy and body solutions limit to those billiard trajectories. That's where we're headed. So then the billiard curves, the trajectories, they're just polygonal curves in E, and vertices on C, right? The vertices all are in here. That's you've hit the table, and you have these rules, huh? So I hit an L and I come out. So I have an incoming velocity and an outgoing velocity. So the rules are simple. This is conservation of kinetic energy. So in this example, if you translate out what that means that the energy before is the energy after. And then the projection onto L before is the same as the projection after. So that's the law of reflection. And in that example, this is conservation of momentum. If you work out what it means in that example, it means linear momentum's conserved. Yeah?
But when you hit the L, then you have to make a choice, right? It's
Okay,
not
right.
deterministic
That's
anymore.
right. It's not deterministic. So that's the key thing. It's not deterministic, but I'm not thinking of it as probabilistic either. I want to know the space of all paths. That's what I want to understand. But it's not a deterministic system.
So if you take a line, like say, and you hit like that, what's all the possible directions?
Well, it's a sphere of possibilities, huh? This will be a, so I think I just kind of draw the example like this, or you can draw it here, huh? There's a circle's worth of, you come in, there's a cone of possible guys coming out. So, so given V minus,
One generator and the outcome from the other.
okay, so given a V minus coming in, there's a sphere worth of V pluses, yeah.
This trajectory is extrema of
That's going to, yes, that's going to be a theorem, that's going to be the punchline. You got the punchline, Serge. That's good, I knew you would. Okay, so that's the setup. Other questions?
One question. So
Yes, please.
when the energy is fine, when you don't quite hit the collision, then you kind of turn around almost you almost turn around, right? When
You're talking about in the n-body case?
Yeah.
Yeah, so this is wonderful. Everybody's guessing the questions that come up. So all right, so let me draw a little picture of Andreas Knauf's intuition. So if you look at the two-body problem, so Kepler, the solutions for energy positive, the solutions look like hyperbolas, yeah? And when you get very, very far away from a hyperbola, it starts limiting to a picture like this, huh? So that's the essence of his intuition. Now, he doesn't care if it's repulsive or attractive. He studied the repulsive case a lot. So,
The angle is not, you don't turn around by.
so this depends on energy and initial and an impact parameter coming in, yeah? But the idea of the theorem was to, what we think is a theorem is, so if you have, it's going to be something like this. Given a billiard curve, Q of t, you want to find a family of n-body solutions. They're going to have positive energy. And he doesn't care positive, negative, with, I'll call them x of, and there'll be some other parameter, like some initial condition parameters, I don't know, like c, and the right limit is 1 over lambda x, lambda t, and then you have to put a lambda here, and these should converge to q in some sense. So that turns out to be the right. So this isn't proved yet. This would be kind of theorem 2. Andreas is certain that it is not going to be a problem.
This is for the Kepler potential.
It's for any. You know, the way the paper's written, it's kind of like any 1 over r squared, probably any power law. Yeah. So the idea is by changing kind of the impact parameter, you can change. Basically, the idea is from far away, all that's left is conservation of kinetic energy and linear momentum. That's the idea. Yeah. Other questions? Okay, so I want to tell you the two theorems that are out there about this situation. So this Burago-Ferleger-Kononenko, 1998. The number of collisions is finite. In fact, there's a number lambda that depends only on the inner product and the collection, and there are less than or equal to lambda collisions. So that's a surprisingly hard theorem. So that's okay. So now, what I want to do is, given that, imagine fixing.
So I'm not trying to understand the statement.
Okay, so I fix this bunch of subspaces,
Yes?
and I have these rules. These are, and I look at any trajectory that satisfies that rules. Any polygonal path that satisfies those two rules.
And this is even if the L's are hyperplanes? Or?
They are, yeah, even if they're hyperplanes, especially if they're hyperplanes, yeah. In the hyperplane place, it was done before by Sinai.
Really nasty.
They're not affine, they're linear. If they're affine, it's definitely false. You could take two parallel lines. So these are linear subspaces.
Oh, through the order.
They're all through the origin. So they're in the hyperplane case, they're very good. Thank you. Thank you.
Something through.
Yeah. Good. Other questions? Okay. So imagine fixing, Andreas, he's from Germany, he calls it a train correspondence. I call it an itinerary. So in other words,
So what is it like for 3 lines in 3 space, like as you said?
what is what?
The lambda.
3. No, 2. 2 if they're perpendicular. I'll do that for you at the end if there's time. 2 if they're like this, huh? Okay. So, right. So what I want to do is I want to say that first I hit L1. Let's see, where do I draw? I'll draw it over here. So yeah. So imagine that I say first I hit subspace 1, and then I come in and hit 2, and etc. Okay? And then I finally hit LK, and then I sail off to infinity. Okay? So I'm going to call that an itinerary, and I'm going to do it like this. So I have a L1, and an L2, and an LK, and I have times T1, T2, TK. And for purposes of the proof and the minimization that's about to come, I'll have a later time TK plus 1 where there's no collision, and an earlier time T0. And these are strict inequalities. It's important that I don't allow things to become equal. And so I insist then that Q of Ti is in Li. So I fix the itinerary, and then the question is, what is the space of all trajectories with that itinerary?
Fix the times.
No, don't fix the time. You just fix the itinerary. You insist that the times don't become equal.
Can Li repeat?
Yes. But they can't repeat one. You can't have L1, L1. That's not going to be allowed.
You have to hit everyone.
No, I don't care. So that was why I didn't want to. This could be a very small subset of this, huh? You don't have, it could be just 2 of them repeating, for example.
So the subspaces could have non-trivial intersections.
They, in the n-body case, they do, and that makes things difficult.
You don't allow those in your itinerary?
No, I do.
Oh, you do?
You
Then-
definitely do.
But when you have a collision, can you collide? at-
No, you can't have an edge lying on the collision locus. No edges lying on the collision locus. I should say that. No edge on C. Because it's too hard to deal with in the 3-body case. I can tell you later, but it's just too hard to deal with. So we do the easy case first. Okay, so the okay. So it's a space of all these billiard trajectories. And there's, there's a group acting on here. There's obviously time translation. Yeah.
You can hit an intersection of L1 and L2.
Okay, so now that's a subtlety. What if you hit an intersection of L1 and L2? That makes a problem for n bodies. Here it doesn't. The trick around it is each time you have a collision, you label the collision point. You see, this could be an LJ also, but you pick one, so they're labeled.
You have to pick one.
You pick one. So pick one. Everybody's coming up with all the subtleties as we go. This is great. Okay. So R acts by Q of T goes to, right? Just shift the origin. Then all these times would just, yeah. And also R plus acts by scaling. Q of T goes to 1 over lambda Q lambda of T. So I'm going to insist that the velocities, I can make the velocities 1 here. This one. Okay. So the question is, although here's the question, what is the structure of B? Sorry. This is to remind me to check where my spare key is on my car. I remember. Okay, what's the structure of B? That's the question that Andreas asked me to work on, and so maybe the best way to explain it is look at over here. There's no collision. So there's an initial line coming in. I'm going to call that L minus. There's a line coming in, and over here there's a line going out. Yeah? So I have two projections. I have a projection these are oriented lines. And I remind you that these are symplectic manifolds. They look like the cotangent bundle of the sphere in E. And you should think of the sphere as being in velocity space. So I put a little v just to remind you it's velocity space. And that's because you've normalized them to be length 1. So I have two projections down. And yeah, so I can now write down the theorem. Right. So theorem 2, and this is by this group of us. B mod, the time translation is a Lagrangian relation on lines, on the lines. So I have to, and a little bit moreover, and pi minus pi plus is a diffeomorphism. Maps this relation diffeomorphically onto, maps B mod R diffeomorphically onto the relation. Okay, so I want to explain those words. So maybe it's easier to explain the last part first. So the last part is saying, so I have an incoming, so we think of it as scattering. That's Knauf's, he's written books on scattering. So you have a line coming in, line coming out. You want to think of it as a scattering map, like in physics. But so the second part of the theorem says, if I know the incoming line and the outgoing line, I in fact know the whole trajectory up to time translation. Remember, that's assuming you fixed the itinerary. So once again, if you know the incoming line, the outgoing line, then you know the whole trajectory with that itinerary. So it's uniquely determined. And I want to say a word about what a Lagrangian relation is here. Okay. So the idea of a Lagrangian relation is that if I had a map, if F, you want to think of it as a map. This is a symplectic space. if you had a map that was symplectic, this has a symplectic structure, its graph is Lagrangian in and Weinstein invented this like conjugation. He puts a bar there. Just you put the opposite symplectic form there. So this has a symplectic form omega. You use the symplectic form omega plus minus omega, huh? So the graph of a symplectic map is a Lagrangian submanifold of the product, and then you just define, that's what a Lagrangian relation is by definition. So R is Lagrangian here. So in particular we know its dimension. Its dimension, the dimension of this space, it's smooth, its dimension is that. Okay? So that's this part of the theorem. Okay? Any questions on that? Yeah. Yeah. Well.
Oh, but you could have the same L minus and two different L pluses. So it's not really.
That's right. It's a relation.
Yeah, right.
That's right.
You could-
There's in fact there's a picture. If I can plug the thing in, I have a picture of exactly that I wanted to show. Yeah. Yeah. You can. Yeah. Yeah. And yeah.
I'm not sure if this is the correct mechanical interpretation, but it sounds very plausible, but maybe completely wrong too. That is, if you take a trajectory, like you put a ring on each line.
Put a little ring on each line.
Right, and take constant tension springs.
Yeah.
And then you can move the two without doing any work.
Yeah.
And that's why the
Yeah.
time is doubled.
Yeah.
Because
Yeah.
is that,
Yeah. That's the right. That's it. Yeah. Had you on as a co-author, Mark. Okay, so let me, the method of proof is basically what you just said, so I'll go through the method of proof. Okay.
Richard, we're almost crowdsourcing this paper.
Let's see, I should end in 5 minutes, is that correct?
About 8 minutes.
10 minutes, okay. But maybe another question about you had a question.
I asked already.
Oh, okay. So I'm going to erase the statement. Yeah, I'll erase the statement. No, I'll erase this. I don't want to erase this, but I'm going to erase it. Okay. Okay, so what I'm going to do for the purposes of the proof is I'm going to think of fixing a time over here, and I'm going to call it A, and fix a time over after all the collisions, and I'm going to call the corresponding point B. So these are non-collision points. And now I'm going to look at the path length that I have. So I have well, let's make first S. S of what? Of Q0, Q1, up to QK, QK plus 1. That's just the path length. Well, let's start writing it down. Q0 minus Q1 plus Q2, Q1 minus Q2. Okay, so that's just the path length. And these paths are going to be extremal, which is what you were saying with your rings, Mark. So, and now we fix Q naught is A, QK plus 1 is B, and then you have an SAB, huh? Okay, right? And now, so then you just do a computation. The critical points of SAB, I'll call it lambda. This equals 0 if and only if A lambda B is a billiard trajectory. Okay, so that's a computation. You just, if anybody has done anything with generating functions, you've seen cancellations. You just compute and you see it, so the normals have the right property. You have to remember where these vary. Lambda, which is Q1 up to Qk, is varying in L1 cross L2 up to Lk. Yeah? That's where that varies. So that part's a computation. And then there's a little bit of technicalities, like what do you do if they lie on the same subspace and things like that. But let me just leave it like that. And then, so that's kind of the first part. And then you look up something I've always wanted to learn about and never had to use in a paper. People call them generating families. Arnauld loves them. My French friends, of course, say it's due to other people, Hormander, and anyways, it's very, I didn't trace the history down. Some people call it Morse families. So this is a generating family. So let me just tell you what it means. It means this thing is the generating family. So basically, half the theorem comes from this being a generating family. So my grammar is backwards. The S is a generating family, okay? And what that means is that if I set VA equal to minus ds dA, so now A is Q0, and VB is ds dVB, dB, differentiate with respect to the last guy, and then set all the other derivatives 0. Let's just say ds dqi equals 0. Okay, so this defines a bunch of equations. And you're guaranteed that it's Lagrangian. There's a problem with whether it's smooth. So you want to do the implicit function theorem. So guaranteed Lagrangian where smooth. And let me write down the smoothness condition is an implicit function theorem. So implicit function theorem condition, I'll write it this way. So there's a Hessian condition that you need to check. Some Hessian is non-zero, and then you get that this is locally a Lagrangian graph. So this was the hard part. This was where the work is. This was, for me, the hard work was this, those 3 or 4 pages of linear algebra. So that gives you the things locally Lagrangian. And now I want to explain the uniqueness, and that's where these CAT 0 spaces come in. So this is kind of the local picture. Global uniqueness uses some ideas that I didn't know about. Maybe some of you do. And I learned this from the paper that I told you about by Burago. I just say BFK, these guys. So let me quickly tell you the idea, and I'll tell it to you with regular billiards. Imagine you have a simple billiard problem in the plane with a convex body, and you want to understand that simple kind of billiard problem, huh? So here's a convex body K, and this is you can think of this as the plane if you want. And what you do, we're going to make a new space we're going to glue 2 copies of E together along K. So I take a picture, a copy of E, which I'll call E0, and another copy that I'll call E1, and I glue them together metrically along K. So the best way I can do it is kind of have them come in like this. So what does that mean? That means, so you can literally just glue them. And so geodesics, if I have 2 points in here, geodesics are the same. If I have 2 points in here, geodesics are the same. If I have a point here and a point here, I have to pass through here. I have to pass through here to get from here to here. Now, you want to just go like this, huh? But in this construction, you're allowed to go right through the middle. You can pass right through the middle. So in any case, this thing is written E0. So it's a metric. It's non-negatively curved. So you learn a little bit about how to define curvature in spaces that aren't smooth. And it's simply connected. And I got this book by Burago called A Course in Metric Geometry. It's what's called a Hadamard. This is what a Hadamard space is. And they have unique geodesics between any 2 points, just like hyperbolic space. So if I take a point in this sheet and a point in this sheet, there's a unique geodesic connecting them. Non-positive, non-positive, thank you. I want to say negative, but it has 0 curvature, yeah. Non-positive, yeah. Thank you. Okay, so the construction we do for the itinerary business to get the uniqueness is you just glue along all these subspaces. Us. So this is our Hadamard space. The fact that this is Hadamard is, I think I'm saying the name right, Reshetynak. Maybe someone knows. Is that, yeah. So this is a theorem of Reshetynak. So this is what gives us a uniqueness, and I think is a good time to stop.